Hello everyone, our next topic is Harnack's theorem. Harnack's theorem प्रीवियस में हमने किया था कि Harnack's इक्वालिटी क्या होती है. नेक्स्ट है हमारी Harnack's theorem. So before doing the main proof of this theorem, let us recall some fact from the metric space. So first जो रिजल्ट है हमारा वो है कनेक्टेड कंप्लीट metric space. कंप्लीट metric space. सो सपोज करें कि इफ़ एक्स टी भी मेट्रिक स्पेस, ये हमारे पास कोई भी मेट्रिक स्पेस है एक्स टी, देन दिस एक्स टी इज कॉल्ड कंप्लीट. दिस एक्स डी इज कंप्लीट मेट्रिक स्पेस इफ एवरी कोसी सीक्वेंस in X is convergent as well. So a XD metric space is said to be a complete metric space if every Cauchy sequence in X is also a convergent sequence. हमें पता है कि जो convergent sequence होते हैं, हर convergent sequence आपकी क्या होती है, Cauchy. Misconvergent आपकी क्या imply करती है, Cauchy sequence को. But Cauchy may or may not be convergent. So जैसे ही आपकी हर Cauchy sequence X में क्या हो जाएगी, converge कर जाएगी, then this XD is called complete metric space. नेक्स्ट जो डेफिनेशन है हमारी वो है कि सपोज करें कि एक्स डी बी ए मेट्रिक स्पेस, देन इफ वाई इज ए सबसेट ऑफ दिस एक्स, then this y means the subset of x is also called a matrix, a complete metric space if then this y which is the subset of x is called complete if and only if this y is closed. Means every closed subset of a complete metric space is also a complete metric space. And the third जो रिजल्ट है हमारे पास वो है हमारा कनेक्टेड सेट. एंड सेकेंड इसके नेक्स्ट हम करेंगे क्लोज. किसे बोलेंगे, क्लोज सबसेट. सपोज करें कि y एक सबसेट है x का, देन दिस y इज सेड टू बी क्लोज सबसेट ऑफ x इफ एवरी sequence in y which is converging, suppose it converging to a point y naught or a function y naught, then this converging point must belong to the set y. So this y naught must belong to the y. If the limit of every convergent sequence is also in y, then this y is called closed. If y satisfy all these conditions, then this y is closed. नेक्स्ट है हमारा कनेक्टेड सेट. सो सपोज जी बी एनी सेट, देन दिस जी इज सेट टू बी कनेक्टेड सेट इफ इट इज नॉट पॉसिबल टू राइट जी एज ए यूनियन ऑफ टू disjoint open set. मीन्स इट नॉट पॉसिबल टू राइट जी एज ए यूनियन ऑफ टू disjoint open set. मीन्स जी कनेक्टेड है and if G is the union of two disjoint open set, then either A is equal to phi or B is equal to phi. Means G connected set होगा if it is not possible to write G as a union of two disjoint open set. And if someone says that G is a union of two disjoint open set, then this condition implies that either A is equal to phi or B is equal to phi. So this is the definition of connected set. Next we have compact set. कोई भी सेट है कि this set key is said to be compact if every open cover of that set G has a finite subcover. Means corresponding to every open cover we get a finite subcover. Then this key is called compact set. सो जो हार्नॉक्स थ्योरम है हमारे, एक जो नोटेशन यूज होगी वो है आपकी हार्नाक ऑफ जी, एंड दिस रिप्रेजेंट द कलेक्शन ऑफ ऑल होलोमॉर्फिक फंक्शन ऑन जी, एंड दिस जी इज रीजन. As I already told you the difference between the domain and the region. So this G is domain with some none or all boundary point. Means if we consider the boundary of the domain as well with some, none or all point, then the domain is called region. So this G is the region. Here this HARG is the collection of whole holomorphic function that is defined on the region G. नेक्स्ट नोटेशन जो है हमारी वो है CGR. दिस इज द नोटेशन फॉर द कलेक्शन ऑफ ऑल सबसेट, ऑल कॉन्टिन्यूस सबसेट दैट इज डिफाइंड फ्रॉम G to R. मीन्स CGR हमारा पास क्या होगा, CGR द कलेक्शन ऑफ फंक्शन एंड सच दैट दिस फंक्शन इज डिफाइंड फ्रॉम G to R एंड कॉन्टिन्यूस एज वेल. So this is our CGR. In Harnack's theorem, the first part is that we have to show this HARG, this Harnack of G is complete, and this CGR is already complete, and this HARG is the subset of CGR. Because in CGR we have a collection of all continuous function that is defined on the region G, and HARG the harmonic function means whose second derivative exists and continuous. So first derivative also continuous, so HARG is contained in CGR. So and this CGR is complete. Now we have to show this HARG is complete. So it is sufficient. To show that this HARG is closed. If this HARG is a closed subset of a complete metric space, then this is also complete metric space. And to show the closed, we take any arbitrary sequence in this HARG and we show that its converging point also belong to that set, and that's complete our proof. So Harnack's theorem क्या बोलते हैं, let G be the region, then first condition we have to show metric space HARG is complete. सेकेंड कंडीशन है हमारी, इफ़ UN is a sequence in HARG such that it is a increasing sequence, means U1 less than U2 less than U3 and up to so on. So this is the increasing sequence. Then we have to show then this sequence either converging to infinity uniformly on a compact subset of G, or if it is convergent then it converging to a harmonic function. Means we have a sequence of this UN is an increasing sequence, and we know that the increasing sequence which is bounded above, then it must be convergent, and if it is not bounded above then it divergent. So there is no concept of monotonic sequence. So increasing sequence क्या करेगी, either converge करेगी और diverge करेगी. So second condition हमारी क्या कह रही है, if it converges then it converges to a harmonic function, and if it divergent sequence then it diverge uniformly on a compact subset of G. Means in the given region G we have to take a compact subset like an open ball, not open ball, we have a closure of ABR that is open and that is closed and bounded, so we can say this is a compact. So corresponding to given region we have to take a compact set that is BAR closure. So by we are not considering over the whole region, but inside that region we always consider a compact set, and then we study all the property on that compact set. So this is our Harnack's theorem. तो first जो part है इसका, to prove the first part we know that this CGR is a complete metric space and HARG is contained in CGR. So this is complete and HARG is a subset of CGR. So to prove HARG is complete, it is sufficient to show that this is closed. And to prove closed, we have to take any arbitrary sequence, convergent sequence, and its converging point must belong to the HARG. Now as we know that this CGR is complete metric space and HARG is subset of CGR, therefore to prove HARG is complete, it is enough to show that HARG is closed subset of CGR. So now we prove this HARG is closed. So for this let us consider a sequence in HARG such that this sequence converging to the point U. Since this UN belongs to HARG and this contains CGR, In CGR we have a collection of all continuous function that is defined from G to R. So this is the sequence of continuous function, and in the region we consider always a compact set of the form B closure AR, and we study all the property of that sequence on this set, not on the region G. So this is the sequence of continuous function, and it is converging to U, which is also a continuous function, and we are studying over the compact set that is closed, so we can talk about the uniform continuity. So this UN is belongs to CGR, but CGR is a complete metric space, and this UN converging to U, and that U is also a point of CGR. Then therefore this UN converge but uniformly to U, because in the region G we consider the compact set, and the sequence of continuous function that converging to a continuous function inside a closed or bounded domain, or we can say inside only a closed set, then we can talk about the uniform continuity. So then this sequence is uniformly continuity to U in CGR. So, and this uniform continuity give us the guarantee or the permission to interchange the limit and integration. So we can interchange limit and integration such that limit n tends to infinity U1 can be written as integration limit n tends to infinity U, and this interchange by uniform continuity. Further, let us consider this B closure AR be the closed disk which is contained in the given region G. Then since its UN is harmonic function, and so it will satisfy the mean value property, because in HAR we are consider all the harmonic function that is defined on a G. So since this UN is harmonic, this is the sequence which comes from the HARG. So each element of that sequence is harmonic as well. So each harmonic function, as we already know, satisfy the mean value property. So U and A can be written as 1 upon 2 pi integration from minus pi to pi U and A plus R e की power iota theta d theta for all n belongs to natural number, because for the sequence we have a domain is the set of natural number. Now let us apply the limit on this above equation. This gives us limit n tends to infinity U n is equal to 1 upon 2 pi limit n tends to infinity minus pi to pi. This is U n A plus R into e की power iota theta d theta for all n, and again we can interchange this limit and integration due to uniform continuity. So as this U n sequence tending towards the point U, so whenever we apply limit it tends towards a point U, so it will become U of A, which is equal to 1 upon 2 pi minus pi to pi. We are interchange here limit and integration, so we get limit n tends to infinity U n A plus R into e की power iota theta d theta and for all n. So again this quantity will be equal to which converging to a point U, so it will become U A plus R into e की power iota theta. So finally we get this U A is equal to 1 upon 2 pi integration from minus pi to pi U A plus R into e की power iota theta. So we get this U is satisfy the mean value property, that's why this U belongs to HARG. So we shown that this we consider a sequence of harmonic function which converging to U, and that U is also a harmonic function, means the converging point also belong to that set. That's why we can say this HAR is closed, and if this HAR is a closed set, then we can say this HAR is complete. So this complete the first part. Second part, in the second part we have to consider a increasing sequence, and we have to show that if this sequence is convergent, then it converging to a uniform harmonic function, and if it divergent, then it diverges to a uniformly on the compact subset of the region G. So in the second part we may assume that this U1 is greater than equal to 0, and let us consider UZ. Here we define UZ, which is equal to supremum of U and Z for all n greater than equal to 1 and for each Z in the given region G. Then for each Z in G, we have either this UZ is equal to infinity, or this UZ is belongs to R, means is less than infinity, is give us some finite value, and let us consider this sequence converging to a point U. Then again define two functions. First function is A such that it is the collection of all those points of the region G for which uz is equal to infinity, means we have to collect all the points of the region G for which we get infinite value. And the second is B. This B contain all the point of the region G for which uz is strictly less than infinity, means it gives us a finite value. So it is very clear that this A union B gives us the whole region G, and in this in this set A we consider all the point for the point which we get the infinite value, and in this set B this is the collection of all points for which we get finite value. That's why we can say this A intersection B is equal to phi and G is equal to A union B. But as we already know, this G is connected set and it can be written as a disjoint open set, as a union of disjoint open set. So we can say this either A is equal to phi or B is equal to phi. But before that we have to prove this A and B are open set. So you have to prove by your own. Firstly you have to show A is open, then you have to show B is open. Next we have to consider, since G is given as a region, G is the region, so this G is connected because region क्या होता है, region is a domain in which we consider all, some or none point of the boundary. So it is connected. If we have given a region, then it is connected. So since G is connected and it can be written as a union, and it is the union of two disjoint open set, that's why you can say either A is equal to phi or B is equal to phi. So now from here we consider two different cases. First case for which A is equal to phi and the second case for which B is equal to phi. So if A is equal to phi, then the region G is equal to B, and if B is equal to phi, then the region A is equal to G. Suppose B is equal to phi, then the region A is equal to G, then U is equal to infinity, because A has a collection of all those points for which U is equal to infinity. Also, if B closure AR is contained in the region G and rho is a radius of a circle for which is greater than 0 and less than R. Now consider a value R minus rho and R plus rho, consider as a capital M, which is greater than 0. So the equation third, which is the Harnack inequality, the left side of this inequality gives us M into U and A less than U and Z for all Z minus A less than rho. And this U and A, this A is the point of the set A for which we get the infinite value. That's why this quantity tending toward infinity, and this is the smallest one. So that's why U and Z tending toward infinity. Hence this U and Z tending towards infinity uniformly. Why we are consider uniformly? Because we our set under consideration is B closure AR, that is compact sets. That's why we talk about the uniformly continuity. So this U and Z tending towards infinity uniformly for Z belongs to B closure A rho. Thus we have shown that for each A and G there is a rho which is greater than 0, such that this U and Z tending toward infinity and uniformly for Z minus A less than rho, that is the compact subset of the region G. Again we have to suppose this B A is equal to phi. In that case the region G is equal to B, and in the set B we have the collection of all those points for which we get finite value. So this uz less than infinity for all Z belongs to G. If rho is strictly less than capital R, then there is a constant n which depend on the point A and the radius rho, such that M into U and A is less than U and Z, and then it is again less than equal to n into U and A. For the region, and here we consider a closed disk Z minus A, which is less than equal to rho. This rho is the radius of the disk. So if M less than n, now consider a sequence mode of U and Z minus U and Z. Our purpose is to show that this sequence is Cauchy sequence. So for this sequence is less than equal to n into U and A minus M into U and M, and we can take M and N such that is less than equal to C and M is less than equal to C. Because M are finite value, so we can always get a constant for which M and N are less than. So consider that point is C. So this is C, U and A minus U and A, and A is the point of the set B. That's why this difference is going to be very small. Let us choose this small quantity is epsilon by C, and this C is cancelled out, so we are left with only epsilon. So finally we get the modulus of UNZ minus UMZ is less than epsilon. So from this we can say this UN, that is the sequence under consideration, is the Cauchy sequence. And if it is the Cauchy sequence, and we already know this HAR is complete metric space, and by the definition of complete metric space we can say this UNZ is a convergent sequence. And from the part first we consider this UNZ is a convergent sequence which converging to UZ, and this HARG is complete, then this UZ is also harmonic. So that's complete our proof. Next we have a green function that we have. This is the last topic of unit second, accept a monodromy theorem. So this is the green function. Let G be a region in the given plane, and let A be any point of that region. A green function of G with singularity at A means we have to consider those points of the region for which this function is not analytic. So if it is not analytic, then that point is the point of singularity. So this is a singularity point, and it is a function defined as G of A from G to R, that is from region G to R, with the property, first property is G is harmonic in G minus A, and the second is Gz is equal to GAZ plus log of modulus Z minus A is harmonic in disk about A. And the third condition is if limit Z tends to W, GAZ is equal to 0 for each W on the boundary of the region. And this green function may not exist for each region, but if it is exists, then it must be unique. This is complete. This is the last topic of our second unit, and with this we complete the second unit, and in the next one we start third one.